Hey guys, today we're going to classify real numbers. So a real number is any rational or irrational number. An irrational number is a number that cannot be written as a fraction, which means that it has a decimal that goes on forever, and that decimal doesn't repeat. On the other hand, we have rational numbers, and those are numbers that can be written as a fraction. They can still have decimals that go on forever, but there will be a repetitive part of the decimal. Integers are any positive and negative numbers without any decimals. Then we have whole numbers, which are positive integers, and then we also include 0 as a whole number. And then the last classification would be natural numbers, and those are strictly positive whole numbers. So here's kind of a little table that represents all of our real numbers. So anything you can think of would be a real number, and then we split it into irrational and rational. So an example of irrational numbers would be pi, the square root of 5, and then the square root of 21, square root of 43. Any square root that doesn't come out nicely. Then we have rational numbers. That is any decimal that ends or repeats, so 0.7, or it could be written as a fraction, so 1/4. We can have negatives as well. Then we go to integers. Integers are positive and negative numbers without any decimals, so 12, 1, -18. Whole numbers, the smallest whole number would be 0, and then any positive number after that. And then natural numbers are very similar to whole numbers. We just take out 0, so it's any positive number. So I would like I guess we'll do one together. What's the most specific classification of a particular number? So if you look at the number 12, and then look back to that table or our definitions, we know that the smallest or most specific classification for 12 would be that it's a natural number. So I want you to classify what's the square root of 11, and then what's the classification of -3. Okay, moving on, we're going to discuss what a set is. So a set is just a collection of objects, and within each set we have elements. So for example, if this is a set, it always has curly brackets around, and then all of these numbers inside of our brackets are elements, so elements of our set. A finite set is just how it sounds. There's a finite number of elements, so we can count the number of elements in it. On the opposite spectrum would be an infinite set, which means there is an infinite number of elements, and we denote that with just an ellipsis at the end, so 3 dots, so it goes on forever. And then on the opposite end, we have an empty set, which means we have a set with 0 elements. So that is denoted with empty brackets, or like a little 0 with a slash through it. Within sets, we can have a couple different things happen. We can find an intersection, and that means that there will be 2 sets that share elements, and we use this little horseshoe kind of symbol. Then we also have what we call the union, which is when we have elements in one or the other set, but not necessarily in both, and it looks like a little U without the tail. So we'll look at an example. Here's 2 sets, A and B. They have multiple different elements in them. If we look at A intersect B, we're looking at all the elements that are in both A and B. So they share 2, 4, 6, and 8. Next, we can look at A union B, which means just an element in either one of the sets. It does not have to be in both. So for your union, you just list off all of the elements. But notice here we don't repeat 2 twice. Or 4, we only rewrite that once in the union. So knowing that these are our 2 sets, we have L and M, I'd like you guys to find the intersection. L intersect M. Okay, moving on. We also have something called closure when we talk about sets. So if we have an operation that occurs between 2 elements in a set, if it's closed, then our result will be another element in the set. So what that means is if C is our set, we have 0, 1, 2, 3, and 4 within that set. I can take two elements, 1, 2, add them together, and 3 is in our set. So this set would be closed with addition amongst those two numbers. Okay. Another more generic one would be multiplying two integers results in another integer. So multiplication with the integers is also a closed set, because no matter what two integers you multiply together, you'll always get another integer. Our next vocab word is a counterexample, and a counterexample is just one example that proves a statement false. So we can look at a closure statement. So all whole numbers are closed under subtraction. So somebody's stating this and they think it's true. Well, we can come up with a counterexample to prove them wrong. So whole numbers, remember, are zero, include zero and then positive integers. So a counterexample would be 2 minus 5. We know it has to be subtraction because that is what the statement said. So 2 minus 5, both 2 and 5 are whole numbers, but when we subtract them, we get negative 3, which is not a whole number. So that would be a counterexample, which proves that statement false. Another example would be like 7 minus 17. So you could choose any two numbers that results in a negative number to be your counterexample, but it only takes one counterexample to prove something false.